In the last video, we developed a formula for how to find the arc length along the curve of some function. We have that the arc length equals the integral of dl, and dl can be either of these two expressions, depending on whether we want to integrate with respect to x or with respect to y. Let's try some more examples of applying this formula. For example 2, we want to find the arc length along the curve of y equals 2/3 x to the 3/2, and we'll go from x equals 1 to x equals 3. Now, we need to decide here which expression for dl will we use, and we have two choices. We have either dl equals the square root of 1 plus the derivative of y with respect to x squared integrating with respect to x, or we could choose the other expression where we integrate with respect to y. That's 1 plus dx over dy squared dy. Which of these two expressions will we use? Technically, we could use either one, but we have y expressed as a function of x. That will allow us to solve for dy dx, and we have x values for the limits. So we are going to choose this first expression integrating with respect to x. Let's work through the steps. So our function is y equals 2/3 x to the 3/2. We're going to use the expression for dl, the square root of 1 plus dy dx, quantity squared dx, and we're going from x equals 1 to x equals 3. So our first step will be to find the derivative of y with respect to x. We're taking the derivative of 2/3 x to the 3/2. We can use the power rule here for derivatives. So we have 2/3, bring the power out front, 2/3 times 3/2. This is convenient, that will simplify to 1. And then this is x to the 3/2 minus 1. 3/2 minus 1 is 1/2. So this is x to the 1/2, which is simply square root of x. That's the expression for dy dx. Now the arc length is the integral, again, using this expression for dl. So we integrate the square root 1 plus derivative of y with respect to x squared dx, and we'll be integrating from some x value a to some x value b. Here the limits are from 1 to 3, and we have 1 plus dy dx squared. Well, notice how convenient this is. We have dy dx squared, so when we square that, we simply get x. We can find the antiderivative here by using a simple u substitution. So we can view this as u to the 1/2 power, and I'll go ahead and not work through all the steps of the substitution because this is a fairly simple one, but in case you want to, I would encourage you to work through the steps. We'll choose u equals 1 plus x, but here's what we get. We have u to the 1/2, so this would be u to the 3/2 divided by 3/2, so multiplying by 2/3, integrating from 1 to 3. So we have 2 times, insert 3 for x first of all, so we have 1 plus 3 is 4 to the 3/2 divided by 3, minus, and then we input 1 for x, so we have 2/3, 1 plus 1 is 2, so times 2 to the 3/2. And this is approximately equal to 3.45. Now, just so that we're really comfortable with exactly what we found in this problem, let's go ahead and look at the graph of this function in Desmos. So here's our function 2/3 times x to the 3/2. It's not the most fascinating looking function, but if we look at the function from x equals 1 to x equals 3, we get that portion of the curve. And we found that the length of that portion of the curve is approximately 3.45. Let's work through example 3. We want to find the arc length along the curve of this function from y equals -1 to y equals +1. Now, once again, we have the choice here whether we want to integrate with respect to x or with respect to y. In example 3, notice that we have x defined as a function of y, and we have values of y that denote where the curve starts and stops. So for example 3, we will use the second expression for dl. We will integrate with respect to y. So to begin with, let's see if we can visualize our curve. We're told that x equals the square root of 1 minus y squared. If we imagine squaring both sides, we could get x squared equals 1 minus y squared, and this would produce x squared plus y squared equals 1. Hopefully we recognize this as the equation of a circle. So we're working here with a circle, and x is defined as the square root of 1 plus y squared. This must always be positive. So this is half of the circle in the positive x direction. So it looks like this. This is a circle of radius 1, so we have y equals positive 1 here, and y equals negative 1 here. Those were given as the y values to denote the entire curve. So we will be finding the length of this curve from y equals negative 1 to y equals positive 1. Now, what is this? This is simply the circumference, or half of the circumference, of a circle of radius 1. So what's the circumference formula for a circle? Circumference equals 2 times radius times pi, diameter times pi. And in this case, we're finding 1/2 of this circumference. So this arc length here, we would expect to be 1/2 of 2 times the radius 1 times pi. Well, 1/2 times 2, those would cancel. So we have simply radius times pi. The radius is 1. We expect this length to just be pi. That is the arc length of this curve. Now we know that from geometry, but let's see how to get there using our arc length integral. So arc length L is the integral of dl, and for this example, once again, we wish to use the expression for dl, 1 plus the derivative of x with respect to y, quantity squared, integrating with respect to y. Our limits will be from y equals negative 1 to y equals positive 1. Now, x equals the square root of 1 minus y squared. So let's find dx dy. We need to take the derivative here. So we find dx dy. That is the derivative with respect to y of the square root of 1 minus y squared. Now, this requires the chain rule. First, we need to find the derivative of the square root and then multiply by the derivative of the inner function here. So the derivative of the square root is 1 over 2 square roots, and we have the inner function 1 minus y squared. Now we multiply by the derivative of the inner function. The derivative of 1 is 0. The derivative of y squared is 2y. This is negative, so we multiply by negative 2y. Notice that we can cancel these 2's. So we can write this a little bit more simply as y, negative y, divided by the square root of 1 minus y squared. That is our expression for dx dy. That is what we will put into the arc length integral. So in the integral, we're still integrating from negative 1 to 1. We have the square root of 1 plus this expression squared. Now if we square this expression, the negative goes away. We're squaring negative y, that's simply y squared. When we square the denominator, the square root, that also goes away. So if we square the derivative of x with respect to y, we obtain y squared divided by 1 minus y squared. Now how do we evaluate this integral? This looks rather complex. Let's work through the steps because this is really good practice. First thing we want to do here is to simplify under the square root. So I'm going to get common denominators here. So I'm going to convert this 1 to be 1 minus y squared divided by 1 minus y squared. That'll give me common denominators and allow me to add underneath the square root. So the 1 I write as 1 minus y squared divided by 1 minus y squared plus y squared divided by 1 minus y squared with respect to y. Now I can add these fractions together. So I add the numerators now, and I have 1 minus y squared plus y squared, while the y squareds cancel. So this is the integral of the square root of 1 divided by 1 minus y squared. Now, when I take the square root of the fraction, I could write this as the square root of 1 divided by the square root of 1 minus y squared. So this simplifies a little further. It's the integral of 1 divided by the square root of 1 minus y squared with respect to y. Now at this point, I hope that you recognize this integral. The antiderivative of 1 over the square root of 1 minus y squared is arc sine. So this equals the arc sine of y. The antiderivative is arc sine of y, integrating from negative 1 to 1. So we have arc sine of 1 minus arc sine of negative 1. Now, what is the arc sine of 1? Well, let's think about the unit circle here. And we want to know what is the angle that gives us a sine of 1. Well, the angle that gives us a sine of 1 would be this angle right here. This is pi over 2. That gives us a sine of 1. So sine of pi over 2 equals 1. This is exactly the same as saying that arc sine of 1 equals pi over 2. Now, where do we have an angle of -1, or a y value rather? Where do we have a y value of -1? That happens right here. So -1, this angle is negative pi over 2. So we could say that sine of negative pi over 2 equals -1. This is the same as saying that the arc sine of -1 equals negative pi over 2. So in this integral, we have pi over 2 minus negative pi over 2, using the arc sine values. This is negative, negative, this is plus, so pi over 2 plus pi over 2. This just simplifies to pi. So we found that the arc length here is simply pi, which is exactly what we expected, because geometrically, we are finding half of the circumference of a circle with radius 1. We said that that length is pi, and we just confirmed it using calculus. This is actually rather interesting. We could generalize, and we could find an expression for a circle of radius r. We could find the arc length really using pretty much the same steps, just a little bit more in general. And we could actually prove the circumference formula for a circle using calculus. Isn't that fascinating? We can prove that the circumference of a circle is this formula here just by using integration. I think that's really cool. Finally, let's work through example 4. We want to set up two integrals, one with respect to y, one with respect to x, to compute the arc length of the curve y equals natural log of x between these 2 points. We won't actually bother to evaluate these integrals, we'll just set them up, but we'll do this with respect to x and with respect to y. So first, let's go ahead and graph the natural log function. This is a graph we want to be very comfortable with. We want to be able to give a rough sketch. It looks something like this. Y equals natural log of x, and we are finding the arc length from 1, 0, that's this point here, to e comma 1. E1 is about right here. This isn't a perfect picture, but it'll give us a rough idea of what we're finding. So we want to know the length of this curve, and we will set two integrals up, one with respect to x, one with respect to y, to give us this length. So here we'll have with respect to x, and here on the other side, we'll have with respect to y. Once again, we use the arc length formula. Arc length equals the integral of dl. When we integrate with respect to x, the expression for dl is the square root, 1 plus the derivative of y with respect to x, squared dx. Integrating with respect to y, the expression for dl is the square root of 1 plus dx over dy, quantity squared, integrating with respect to y. All right, first let's integrate with respect to x. We have that y equals natural log of x, so the derivative is 1 over x. So the arc length with respect to x is the integral of the square root of 1 plus dy dx, we just found that that's 1 over x, squared dx. The limits of integration here must be x values. They are the x values that give us this portion of the curve, and the x values are 1 and e. So the limits of integration here are from 1 to e. This integral describes the arc length along the curve. Let's set up another integral with respect to y to calculate the same thing. And what we need first is to find the derivative of x with respect to y. In order to get that, we must solve the original equation for x in terms of y. So we have y equals natural log of x. I want to solve this equation for x. I can do that by taking e and raising it to the power of both sides. So e raised to the y equals e raised to the natural log of x. E raised to the natural log of x, these are inverse functions, so those undo each other, and that just gives me x. So in this case, x equals e to the y. So I've expressed x as a function of y. It gives me the same curve, and now I can find the derivative of x with respect to y just by taking the derivative here. So if x equals e to the y, then dx dy is the derivative of e to the y, which is simply e to the y. Now that I have this expression, I can use my integral formula integrating with respect to y. So here L equals the integral square root of 1 plus e to the y squared, integrating with respect to y. And what are the limits of integration here? They must be y values. So I look at the curve, and I use the y values of these points. My limits of integration are from 0 to 1. Now notice that these two integrals look completely different. However, they are both finding the length of this curve between these 2 points. If we were to evaluate both of them, we would find that they give the exact same numerical value. In fact, the arc length here is just a little bit more than 2. It's roughly equal to 2, not exactly, but both of these integrals give the exact same value. And I'll just mention here that to integrate both of these would actually require quite a bit of calculus. These are very difficult integrals. We do not have the tools to do these by hand. So these require some more advanced techniques. In general, the arc length integrals are rather difficult. So a lot of times we have to do a numerical integration to find the value. So our interest in this section is going to mostly be to set up the integrals to get a valid expression for arc length, and sometimes we won't bother actually evaluating them analytically.